Hello folks. Today we're going to be doing section 8.2, which are basically graphs of the remaining trig functions. Remember from last time, if you were watching, we had graphs for sine and for cosine, right? Basically, if you know sine, you can get cosine. And if you can get those two, then you can get tangent, right? And then there's the other three, cotangent, secant, and cosecant. Let's see. A couple of things. Right. In the packet I would have given you today, and I'll have this again linked in Canvas, there's going to be this page, which is a nice summary. I basically stole this out of our textbook. There's a nice summary basically of the information you already have. Some of it you've written already, but in particular I want to point out this right down here. This relationship is going to be especially important to us right now. They're using the variable t instead of either theta or x. It doesn't matter, all right? I'm not sure why they decided to do that, the author of the book, but just read this as being tangent of x, all right, or potentially tangent of theta, all right? Most importantly, you notice that it is a sine reciprocal, pardon me, it's sine over cosine, all right? Okay. Now, let's do a little review. Right. As for trig functions, what we've done to this point, and where we're going. All right. We have discussed sine, all right, function, all right, which if you wanted to graph it, all right, you would sort of adapt it to, instead of using the Greek letter theta, right, you might use the input variable as being x. It's going to be the same thing. It's going to be an angle, but we'll use an x just because it would be more appropriate on a coordinate plane that's labeled x and y, right? And this, to make it look a little bit more like a function, right, you could either put f of x is equal to this function, or I just prefer personally just saying y because I think it's more plain. The truth is, in order to maintain its status as a function, the trig functions, we would have to confine basically the scope of the graph in several instances. You don't have to worry about that right now. All right, but I'm going to refer to this as a function, all right, and I'm going to label it y anyhow. Then there was this, of course. We had done cosine, rather, which is abbreviated cos. All right, and again, just for the sake of adapting this to something a little bit more familiar, all right, we'll make the input variable and the argument x, and we'll just call this y equals that. All right. So naturally what is coming is the next trig function, as I mentioned, which is tangent, right? So if tangent is normally tangent of theta, again, adapt it to conform to an ordinary coordinate plane. Y is equal to the tangent of x. Right. The most important thing to remember is exactly what I had pointed out. Right. Tangent, right, is the ratio of sine over cosine. And because of that, the graph will be affected. All right, now, just to prove a point, all right, let me refer back to some information you potentially already have. All right. We had been filling in back from section 7.1 and 7.2, a table that looks like this. All right, and I was telling you, what did the trig functions basically translate to? They translate to these ratios, right? If you're looking from the SOHCAHTOA section 7.1 perspective, it's opposite over hypotenuse. All right, if you're looking from the standard position perspective, which is section 7.3, you might call that y over r, r being the hypotenuse, it's the radius of a circle. This comes from unit circles. This is any orientation of a triangle. All right, anyhow, you see these relationships. What is written in black is really what you should try to memorize in the long run. what is written in red is something that you could basically deduce, all right, from this information. All right, anyhow, if you notice, tangent and cotangent are reciprocals of one another. These two where my fingers are, all right? If you look on where my fingers are now, these two are reciprocals of one another. And if you look where my fingers are now, all right, sine and cosine, cosecant rather, are reciprocals of one another. They're just the numerator essentially and the denominator flipped upside down, all right? If sine is opposite over hypotenuse, then cosecant is hypotenuse over opposite, and so forth, right? Another way of looking at it is like this, reciprocal functions. Sine is the reciprocal of cosecant, right? And actually, if I had any sense, I would have completed that parentheses, but hey, not right now. I drew this arrow here because if it were oriented with cosecant here and sine as a denominator, that's just proving that they're reciprocals, all right? If you know these basic three, you could infer, you know, what the remaining three reciprocal functions would be. All right. Anyhow, the ratio, oh, this is what I was getting at. If you notice that tangent of theta is opposite over adjacent, all right, or from standard position in relation to a unit circle, it's y over x, all right? Let's see where that comes from, all right, in terms of the calculation. I'm going to erase this much. If sine of theta, using the labels from section 7.1, right, the abbreviations, is opposite over hypotenuse, and the cosine of theta is the adjacent over hypotenuse, then you'll notice this about tangent of theta, that it's going to be, firstly, sine over cosine, which if you translated each of those things respectively, would be this ratio, opposite over hypotenuse. Still this line. And then just to distinguish it, I'll use black for this ratio. Adjacent over hypotenuse. And you have essentially what would be the equivalent of a complex fraction. Remember, a complex fraction is a fraction on top of another fraction divided. Right. If I erase this just to save space, you'll see what the outcome would naturally be. This, if you think of it as being a division symbol, can be translated to, you know, the typical colon with a line. Right. In which case you have the top feature, opposite over hypotenuse, and the bottom situated like so, right? Then you would treat it as you would fractions, right? Remember how to divide fractions, right? Keep, change, flip. Which means that you would keep the first fraction, or ratio in this case, divided by, multiplied by instead, that's the change, the reciprocal of this fraction. So you would have this instead. Opposite over hypotenuse. This becomes multiplication instead. And those are my markers here. And then you have hypotenuse over adjacent. Keep giving that A a little too much flair. All right. Anyhow, notice what happens. Your hypotenuse number, whatever it may be, is now in this case above the line, and in this case below the line as it was. All right. And there's a cross cancellation effect, as there normally would be. If there was, even if there was numbers here, you would do that intuitively. But it works as well for words, for units, and for abbreviations for those things. So this essentially cancels this, right? Which is why tangent of theta is opposite over adjacent. Okay. Which again, in keeping, just to put this back, in keeping with what we've established already, you see is still true. The tangent of theta is the opposite over adjacent, or you can call it y over x instead. At least if you're talking about unit circles. Okay? All right. So let's see how that affects a triangle. Well, if we had a right triangle like so, and maybe we would be so fortunate as to have a 30, 60, 90. All right, it's 30, 90 is here in this corner, and it'll be 60 degrees here. And we now have established that these would be the side dimensions. The dimension here running between 90 and 60 would be 1. The dimension here would be the square root of 3. And the hypotenuse would be 2. Right? Always directly across from the 90-degree angle. Right? It's the hypotenuse. Okay. How would you calculate sine of theta in this case? All right. Well, if the sine of theta, as we've established, is the opposite over the hypotenuse for any triangle, any orientation, even if it's not riding within the confines of a coordinate plane, all right, we could use SOHCAHTOA, all right? And we could similarly calculate what cosine would be. And now in the context of this section, we could do tangent as well. Opposite over adjacent. Fill in the information. Opposite of, let's just say you did the 30, specifically in each one of these cases, because it would be different if you were using the 60 instead. All right, you'd have a different ratio. It would be these numbers somehow, but it would be a different ratio. Let's do it from more or less the normal orientation, the 30-degree angle, right? As if that was a vertex at 0, 0. What is the opposite of 30? 1. What's the hypotenuse? 2. And there's no more simplifying that, all right? It's 1/2. Let me get this out of the way. The sine of 30 degrees is 1/2. All right. If you had your calculator, and I actually left mine upstairs, all right, and you type in degree mode, sine of 30 degrees, you get the decimal 0.5, which you can always make the calculator switch to fractions if you want. All right. As a matter of fact, let me just run upstairs for a moment, and I'll get my calculator to prove that that is true. Be right back. You'll find a lot of times as you're doing these assignments, you have to switch back and forth between degree mode and radians. All right. So we might as well take a moment to go through this exercise. All right. You would have your calculator, whether it's a TI-84 or 83, turn it on. All right. Erase whatever weird stuff you've been doing. This is what I do on Saturdays, right? The math obsessed. You hit mode. I'm going to switch it to, let's see. You see it's highlighting radians right now. I'm going to switch it to degrees. And then quit this. Okay. Now if you type sine which is written over here, sine of 30 degrees, you should get 0.5, because that's 1/2, of course. All right. The sine of 30, be a good guy or lady or person, right? And close the parentheses. And then hit enter. What am I doing now? Why is it giving me an error? I don't think my mode changed. No, here's what happened. My mode did not save to degrees, it's still in radians. I'm sorry. Yeah, gotta hit enter. All right, or else it won't acknowledge that you did this. Mode, okay. Okay, sine 30, now you see that's again. Incidentally, this is maybe a good point that it came up. You see I got a negative and then you got a 0.98, which is nonsense. All right, it's thinking that this is somehow radians still when it should be degrees. All right, so I'll hit enter, and there you see it, thankfully, 0.5, all right, which is 1/2. If you want the answer as an afterthought to be producing what the ratio ought to be, 1/2, what you can do is go to math and then switch it out, all right? It will switch the answer to a fraction. I keep doing this backwards. Okay, there you see 1/2, right? You could have something presented in the style of a half to begin with, all right? But I wouldn't do that in this case. Do it as an afterthought. Okay. Anyhow, let's do the next one. Cosine of 30, all right? In relation again to this angle, what is adjacent next to, more or less, the 30? For our 30, 60, 90 triangle, it would be square root of 3. Just like 1.7 as a decimal. The hypotenuse remains the same, it's still 2, right? And then you have this, right? To write it a little bit more cleanly, the cosine of 30 degrees is this ratio. The square root of 3 sitting on top of 2, right? Which may not be the most satisfying thing in the world because you see that it has a radical, right? But if you get on your screen, you know, some goofy decimal, don't panic, all right? It's just that it's not writing it in this style of a number, radical, right? And to my knowledge, it's not going to unless you have a more sophisticated calculator. Anyhow, if you figure that the decimal for square root of 3 is it's 1.7, something like that, half of that, all right? So it'd be like 0.86 or something, all right? Let's see, all right? You get it to do exactly the same chore, all right? I'm gonna clear this. We'll hit cosine, and then we'll type 30. And you're gonna see the decimal first. If I just remember to enter over here. You get 0.866, that's half of 1.7. Again, as an afterthought, if you want to switch this to the style that is a ratio, you know, a fraction, all right, then go through math and choose the first option that you see here. And you'll see that it presents it as, oh, it can't. Ooh, how about that? Ooh, we hit a roadblock here. Doesn't want to do it, huh? I guess it can't, my calculator doesn't have the software to produce that symbol on the screen as a fraction. What a shame. That's unfortunate, but what could you do? All right, here, let me just, as an afterthought, prove to you that this is correct. All right, I'm going to basically enter something in the style of a fraction. If you're wondering, how did I get here? All right, there's more than one way to do it. Jose always reminds me, unfortunately he's not here, all right, but it's like alpha and then one of these buttons, one of the function buttons. If it isn't function 1, yeah, it's function 1. You see that it says n/d, all right, and then you see that I've made a complex fraction by mistake here. If this is the outcome, 0.866, whatever it is, all right, I just want you to know that it comes from this ratio of the square root of 3 over 2, right? It doesn't, unfortunately, allow you the option, all right, to convert it to a fraction, unless you have a nicer calculator than this, and you're really not expected to. All right, it's just going to keep doing that spitefully. So I just want you to see, all right, that this is the equivalent of this decimal. I'm going to enter the square root of 3 over 2. All right. In the intuitive fashion of square root of 3 sitting on top of 2. And you'll see that it is this decimal, 0.866. Why? Because this is 1.7 approximately and cut in half. That's half of that. Okay? I guess it just goes to show, all right, it is good to be able to do things more or less the old-fashioned way and not simply rely on the calculator to give you an answer because it may have limitations, all right. Anyhow, the last one would be the tangent, all right, and this is really the point of my mentioning it, all right, this one. If you were to fill in this information, what's going to happen is you're going to end up with a radical in the denominator, and we have to fix that situation, all right. In relation to 30 again, what is the opposite of 30? In this case it's 1. But what is the adjacent value? It's the square root of 3. And although this is the correct answer, it's an example of where math, you might say, has kind of an etiquette. You know, it's not based upon reason so much as it is aesthetics. Math people, probably because they were doing this long before calculators, had found it inconvenient to have an irrational number as a denominator. It just makes things much more cumbersome. So what they would do is write an equivalent. Let's just convince ourselves this is an example of math etiquette, if you will. What do I mean by that? Well, you know from experience that although it is possible, we don't like negative exponents. Right? They do arise naturally, but what we do to compensate is that we form reciprocals. So for example, if you had x to the negative 2, right, we would say, well, it would be better to write it as what it translates to, which is x squared. Right? 1 over x squared. Okay. Here again is another example of etiquette. Right? We don't like a radical in a denominator. So what we do to rectify is this. We rationalize the denominator. All right, which basically means we end up writing an equivalent. Fraction. It's going to look different from the thing that we actually ended up with, but it's going to be equivalent, and I'll show you with the calculator that the decimal equivalents are the same. All right. How does one go about doing that? All right. To rationalize, you basically multiply by a convenient ratio of 1. I'm going to erase a little bit of this. As a technique, to rationalize a denominator, multiply by a convenient ratio of 1. And I'm purposely implying that it's going to be a ratio, so there's going to be an obvious top and there's going to be an obvious bottom. But if it's a ratio of 1, this is slightly out of the frame. Let me see if I move this over just a wee bit. That's the full. Press this up just a bit. Okay. Okay, let me do that. that drifts, I'll try to keep an eye on it. A convenient ratio of 1 means that the value of this ratio, whatever is on top, this line, whatever is on bottom, will be 1 overall. That is really what makes it legal. It doesn't change anything but the appearance of the thing that we have, which shouldn't be forbidden to begin with, but when you're comparing those, you'll see why they give you the answer they give you. Okay, so I'll put that here. If we have this ratio to start with, and then I'm going to multiply by a convenient ratio of 1, we must agree off the bat that multiplying by 1 doesn't change the value of something, right? So legally speaking, it's okay, right? If it's a ratio of 1, it would be something essentially divided by itself, right? Again, not going to look like 1, but it will be equal to 1, right? What that usually amounts to is this, not 100% of the time, but for the most part, it's just basically writing the denominator on top of the denominator. So if you see square root of 3 here, you're going to write the square root of 3 here and the square root of 3 here. If you had some other radical, like a cube root, you'd have to be a little bit more strategic than this. It's still the same principle of convenient ratio of 1 that you're multiplying by, but you're not going to get away usually with just simply duplicating what is here. You're not going to have any problems that are cube roots though, all right, or fourth roots or whatever root, all right, in trigonometry. All right, you're going to have this worst case scenario, a square root. So this will work pretty much 100% of the time for this class. All right, square root of 3 sitting on top of square root of 3. Again, that's ugly. All right, square root of 3 is kind of nebulous to begin with. It's 1.7 roughly, but something divided by itself. The only exception being 0, because you're forbidden from doing that. All right, just wouldn't work mathematically. Something divided by itself is still the amount of 1 overall. Remember what I like to tell you, all right, when we're together. You could get away with murder in math as long as you're consistent. So if you're multiplying the bottom by this weird value for convenience, make sure that you do the same thing to the top and everything is shipshape, okay? 1 times the square root of 3 is most concisely written as just simply saying the square root of 3, right? There's no sin in putting a 1 up in front, but it is unnecessary, right? If you wanted to tinker with this, there's 2 perspectives of it, right? You could apply the product rule and get the square root of 9. This is a side note. This is an alternative path here. And you know that the square root of 9 is going to be a certain familiar whole number, right? The alternative perspective is to say, well, there's 2 iterations of this, all right? 2 clones, if you will, all right? That is the same thing as saying the square root of 3 squared. But if you end up with something that is a square root to begin with and then it is being squared, you could safely assume that they're opposite operations and that they cancel one another. The effect will be the same as if you went this route. This cancels this. Anyhow, the bottom is 3. That means that our answer, which is what I was after to begin with, for the tangent of this particular angle, is this. The square root of 3 over 3, all right? Tangent of 30 ends up being that, all right? Again, let's prove that that is true, all right? I'm going to take the initial ratio that I have here in black, 1 divided by the square root of 3. Produce the decimal with our calculator, all right, or mine specifically, and show you that the equivalent that we've created in red here is the same thing. Right, so when you're comparing the answers, like if you look online, if you use Mathway, or if you have the page that is in Canvas that is the odd solutions of the textbook or whatever resource you're using, if you see something that looks drastically different from what should be, just realize it's an equivalent fraction for all intents and purposes. All right, here is 1 divided by the square root of 3. I'm going to write it in the more or less traditional / style of writing it. 1 on top, square root of 3 on the bottom. You see that you get 0.577, whatever it is. Okay? If my equivalent is correct, right, then what I've written, square root of 3 divided by 3, will give the same decimal. Incidentally, if you're curious, when you want to get square roots, remember second, and then the x squared button engages the square root feature. So second, and then you have that. There's 3. Move over, divide, and then whole number 3, and then you have the same thing, 0.577. Okay, that's a difficult hurdle for all of us to get over, humans. All right, something looks drastically different, but it's still the same thing. You know, it's just an equivalent. All right. I wish I had my pens handy, but I don't. Alright, this is drifting out of frame a little bit. Alright. If you had to figure out any of the other trig functions, their ratios, their decimal equivalents, alright, you can, alright, just by taking advantage of the knowledge you have at this point, that the next one would be cotangent, right? If you had to figure out cotangent of the exact same 30 degrees, all right, if cotangent is the reciprocal of tangent, and it certainly is, all right, then what you end up with is this, right? It's, instead of opposite over adjacent, it's adjacent over opposite. Right? It would come from the cosine of theta over the sine of theta instead. Right? And having divided those ratios, you'd end up with this ratio. Right? You have this information really already, but let me point at it. Okay. Put that down. Tangent and cotangent are reciprocals. Opposite over adjacent is adjacent over opposite. In terms of x's and y's, all right, instead of something being y over x, it's x over y. Okay. If you already had this much work completed, 1 over the square root of 3, then when you're trying to figure out what the cotangent of 30 would be, it would just be this ratio flipped upside down, really. It would be the square root of 3 over 1. Because adjacent to 30 is the square root of 3, and opposite of 30 is 1. Square root of 3, and that's 1. Sorry, getting sloppy here. Anyhow, what does that mean as a decimal? That this is going to be 1.7 something into infinity, right? Because that's what the square root of 3 is, and divided by 1 is not changing it, right? Here's proof, right? If you had taken the square root of 3 and divided by 1, what do you get? 1.732, whatever it is. All right. Now you may notice on your calculator, at least this incarnation of the calculator, there are no cotangent buttons, right? There's no cosecant, there's no secant. But if you know that this is the relationship, that the cotangent of the angle is the reciprocal of tangent, then what you could do is type this, which means, I'll do that in this case. We'll type, I'll do it in the intuitive way. Alpha F1, you see that you have n/d. Enter is over here, dopey. 1, scoot down. Now just type tangent. And you can put 30 in here. Close the parentheses to be a good sport, and you're out of there. If this is what cotangent is equivalent to, you're going to see that the decimal it spits out should be 1.7, whatever it is. And indeed it is, 1.732. Okay, so don't get scared that you don't have those buttons. All right? As long as you have that basic information, and in theory you do, all right, you could figure it out. All right, so if you just to reiterate, I'll put this information underneath cotangent here. If cotangent is the reciprocal of tangent, then secant of theta is the reciprocal of cosine, and cosecant is the reciprocal of sine. That's kind of the reason why, no, this is the exact reason why, I wanted to present the information to you in this particular order. I've seen other textbooks not do that, and I kind of scratch my head. You learn sine first, then you learn cosine, then you learn tangent. Why? Because then they're the mirror image of each other from the way down. These are reciprocals, these are reciprocals, these are reciprocals. All right? You could write things more or less in this style if you want to. All right? I kind of cheated for the lack of space. I drew this red arrow because I wanted you to see these are reciprocals. All right? Anyhow, when you're using your calculator, it might just be more practical to think of things this way, because you have a tangent button, because you have a cosine button, because you have a sine button. Just make it 1 divided by that, 1 divided by that, 1 divided by that, and then the angle, whatever the angle is. This information is, again, on this newer handout that summarizes pretty much everything from the last chapter forward, from 7.1 to this point, 8.2. Now we get into some fun stuff, at least I feel. Let me discuss the transformation model briefly, and then I'm going to draw you some pictures. All right. And I encourage you to sort of, if you can, print out the blank coordinate plane that I'm going to have prepped for you, and sort of follow along. You learn things by touching them, you know. So if you attempt to draw something, you'll get more satisfaction out of it, I feel, right, than simply just beep, boop, boop, pressing buttons on a calculator. It's more efficient, certainly, but it kind of circumvents the learning process. Anyhow, here is our function. As for today, this is the most important. We're making x the input variable. It's still the angle. It's just calling it something other than theta. And this is still a function, f of x. I'm just calling it y. All right. We have adapted this transformation model to this point. Put this underneath. Y equals, I'm going to leave a little space to remind myself. Sine and cosine is what we had talked about. So now we're going to talk about tangent. I'm purposely leaving a blank space here because I want to fill in those features that affect the graph. Right? The coefficient up in the front is usually for transformations of trig functions. It's strangely a capital letter, doesn't matter. All right, B, C, and D. This is more or less a summary from last time, except that now the trig function in question is tangent. Right? Anyhow, they still have the same jobs. Right? Putting a number here affects the graph in some way. Right? This is traditionally the vertical stretch. It elongates the graph vertically, or it might squash the graph vertically, compression. In the case of sine and cosine, we call that the amplitude, right? You're going to see from the graphs that you see of tangent and a lot of the other functions that they don't really seem to have the typical wave that is the sinusoidal wave pattern, the obvious wave pattern. We'll have something a little bit weirder, right? So we kind of shy away from saying amplitude when we talk about tangent, right? We're just going to kind of go back to more or less the traditional transformation lingo. vertical stretch. All right. This, again, was the horizontal stretch. Compression factor. Shrink, some textbooks call it instead. I don't know why my blue is dying out today. Maybe that one may be a dud soon. C was the horizontal shift. Yeah, look at the difference, right? That's a lot nicer than this one. Shift. And this is still sort of the vertical shift. It is. Okay. All right, which means that it controls moving the graph left or right. And this controls the graph up and down. Really squeaking that in, huh? Downtown. Alright, remember for cosine, pardon me, I'll just put this reference from last time. For sine and cosine, we call this amplitude. Because they have sinusoidal wave pattern, the traditional sort of wave like that. The tangent graph you're going to see is a little more funky, right? I'm funky, I've always been funky. I feel like, never mind, I'm going to go into it. It's a Saturday Night Live skit that I've watched recently. Alright. Okay. I think that may be enough to move forward. There's little odds and ends I'm going to walk you through as we go through it. Let's see. Alright. Let me give you this much information now. Alright. There are going to be differences, alright? If you compare formulae from sine and cosine period and the tangent period, right? For sine and cosine, the period was this calculation, 2 pi over the absolute value of whatever the b factor is. All right, what you're going to see now, the tangent, is that it's a little bit slimmer. For tangent, the period, which is the amount of time it takes to complete a wave, normally, is going to be just pi over the absolute value of b. All right, so beware of that. All right, let me do one thing. There is another table I'm going to refer to at the end that refers to the interesting thing about tangents is that they have undefined areas. So they have asymptotes. It's similar to when we had reciprocal function or rational functions, we have those curves and then there's an asymptote, a dashed line, where the function would not exist. Right? The tangents have a similar situation. I don't want to give you that information just yet, so I'm going to bite my tongue and then kind of ease into this by doing a calculation with you. there is a table, I'm drawn on it unfortunately, that looks like this, all right? I'm not going to complete the whole table, but in the handouts, again, that I would have given you today, try to, in the links, try to print out this table, because doing this calculation, even just one time, all right, brute force, by hand, you'll understand what is basically going to happen with the graph, all right? So I'm going to try to replicate that and see if I can just kind of talk you through the input, output, and coordinates. I'm going to see, maybe I can borrow the thing that I had created already. I'm going to remove this out of the way for a moment and try to use this graph. Oh yeah, let's see. I'll put it upside down just because I'm using different headings in theory. Okay, how does that look? That's okay. Probably have to add another column here. That's all right. Yeah. See the weird tools that I have? No, not actually, because I don't have the keys. Be right back. Dead air. Nothing worse than that. If you were waiting for me, again, pause the video. Right here. Again, here's the blank that I was mentioning. Try to print out this blank sheet. We're not going to do all of these, but the most important ones. I got my keys. So I get in my closet. And this. That's what I mean by my weird tools. This is probably overkill, but hey. This is my father's. Just gonna add another column here. Where would it be appropriate? Let's say hypothetically here. A little bit darker. This marker is on its way out too. Which is unfortunate, because it means I'm gonna have to get more. Bear with me, sorry. Being very temperamental right now. I want a straight line because I'm not so good at drawing on freehand. There we go, that's a little bit better. Rock and roll. There you go. Nope. Left my red check in the closet there. And what didn't take it yet. Okay, that's why I locked the door. Keys. Alright, here's what we'll do. I'm going to duplicate the headings that I had made. We're going to have an input, which is an x value in our case. Right, and then we'll have the actual function, which I'm going to squeeze in here. And then an output, which is kind of silly for the size of this column, but the output in this instance will be a y. And then we'll think of them together as coordinates, right? Ordered pairs, x comma y. Basically, we're gonna, just this one time, brute force produce the dots in which the graph is comprised. And we'll start with some key features. Right? The function that I would have you write in this section here would be this. Right? The most basic incarnation of tangent is just tangent. Right? An a value would be 1. Right? The other features inside, unnecessary. Don't worry about the B, the C, and the D. All right? I want to give you a feel here. So, let's say that we used specifically these inputs, 0, pi over 6, and I'm purposely leaving these a little bit off, pi over 4, pi over 3, pi over 2. And I'm probably getting myself in trouble, but I'll come back and adjust this for the extra space that I need. If you were to systematically stick these values in place of x's, you could use this much of your calculator to spare yourself having to go through the ratios and all that stuff. Let's see what you get. We put 0 in here, and we're going to have to switch the calculator mode to radians. Pi over 4, pi over 3, pi over 2. All right. We're going to enter it in our calculator as such, right? But I want you, as a side note, just be aware what this translates to. 0 is 0, of course, but if you actually used 3.14, right, 159 for pi, and divided by 6, you would get a decimal equivalent, which is only going to be important if you had to basically do this by hand, and normally you don't have to. But I want you to see, all right, pi over 6 is approximately 0.52, so almost a half, a little bit more than a half. All right, 3.14 divided by 4 is approximately 0.79. Right, there's more digits into infinity because it's irrational. Pi over 3 is approximately 1.05, and pi over 2 would be 1.57. All right, I'm going to do the negative ones just because if you do something brute force, that is, you generate your own dots basically, you kind of want a nice mix of evens and, of positives and negatives. It will fill in and flesh out your graph a little bit nicer. Right. Anyhow, let's make sure that this is correct. All right, we're going to set the calculator to radian mode again. All right, unless you want to convert this to 30 degrees, 45, 60, and 90. There's no sin in that, but let's just have the experience of doing it both ways. So we'll go back to mode. All right, and I have to switch radians. Make sure you hit enter, otherwise you're a dodo like me. It should be flashing. All right, if you scroll out of there, it should be the same. I'm gonna quit. All right, and now we're good to go. All right, now tangent of 0, super easy, right? Watch what happens. All right, tangent of 0. Close the parentheses. Doesn't really have to, but I like to be twitty. All right, you naturally get 0. All right. That means that our coordinate is going to be this. 0, 0. So we're going to strategically place the dot at the location of 0, 0. All right, when we get to graphing. If you did input of pi over 6, right, in radian mode, you would have to use these symbols rather than 30 degrees, which is what it's equivalent to. So you're going to type tangent, right? If you want to get pi, where is it? Pi is over here, over the caret. Hit second, and then pi, and division, and let's see, 6. All right, so There we go, 6. I'm reading it backwards, unfortunately. That's correct, good. All right. And you see what you get. You get this terrible decimal, 0.57. Again, we're going to have to round it, unfortunately. All right. I'm going to write it in the style of a coordinate that uses this as the input variable, but, all right, this is what would happen. Right? This produces, in the same way that that produces, this decimal, right, about equal to 0.57, right, which basically is this ratio. I don't want to get you too scared, right, of 1 over the square root of 3, which you had, I want to say you just saw a little while ago, right? You know that the equivalent of that would be this. Pardon me, 1. Yes, right, this is rationalizing, okay. Okay. This decimal, if you're curious how you would arrive at it, a little even more brute force than what we're doing right now, would be to figure out the tangent of 30 degrees once again, right? I don't want to go through that exercise again, but if you typed in 30, you'd get the same decimal, 0.57. What is that from? It's from the ratio of opposite over adjacent, a 30-degree angle, all right? This would be the situation, once again, where you would have a radical in the denominator, and you go to math hell, right? Because that's just bad etiquette. And it would be alternatively written like this. What is really important, right, is this. When you're writing this for the sake of generating coordinates, 0, 0 being super easy, right, understand that this is going to be pi over 6 for the input along the x-axis, and this is going to be, all right, about equal to 0.6 for the y input, okay? This is the only instance where you basically have to round an irrational number to kind of gauge where it should be in terms of a y value, right? You'll see what I mean when we get to that point. I have to generate the dots, unfortunately, first, right? And I feel it is a worthwhile spending of our time because a lot of times when you're trying to graph something, it's hard to read unless you have some experience. All right. I'll go a little bit faster here. All right, when you enter input pi over 4, right, this is the same as if you did the tangent of 45 degrees. The result of doing that is that you just get, thankfully, a nice whole number, 1, right? Which means, in terms of a coordinate, at the location of pi over 4, right, you would just have to go up to the point of 1 and leave a dot. Let's do one more of these. Pi over 3. That would be the same as tangent of 60. The way it would work out is basically you'd have this. About equal to 1.7 again. How come? Because it comes from this ratio, the square root of 3 over 1. And in terms of a coordinate, at the location of pi over 3, let's use this decimal because it will make it a little bit easier to read. 1.7. Square root of 3 over 1 is about 1.7. Okay, double check something real quick. Yeah, okay, good. All right, one more. Tangent of pi over 2. This is the same as saying tangent of 90 degrees. The way that this would work out, and I'll show you with your calculator first in this case, because this is interesting. If you ended up typing tangent, all right, of, let's see, get pi again, second caret, divide by 2, look what you get. you get an error message. How come? Because this is an example of where the graph is undefined. If you were drawing a curve, right, the curve would not exist at that location, right? It's an asymptote. This is evidence of an asymptote. Specifically, it's a vertical asymptote. Okay, so you're going to have, I'll put this in black. You'll still have this coordinate to worry about, right, at the location of pi over 2, but it would be undefined at that location. Okay, if I went back and did the negatives of these, for the sake of space, I won't erase this. All right, I'll leave it. But let me just show you what would happen. Right. If you use the negative input variable, that is negative pi over 6, you're going to you're going to get a negative value for your output. Right? You'd get a negative here. Right? So at that location, and you could write this a little bit further down, on your sheet, there is actually the place for it, negative pi over 6. Just write the coordinate as being both negative, right? Negative, negative in that situation. Similarly, if you had used negative pi over 4, right, you're going to get negative 1, which means that at this location, negative pi over 4, negative 1, you'll have a dot there. And for here as well. Negative pi over 3, you're going to get negative 1.7, right? And these would be negative, right? If you did negative pi over 2, what you're going to see is that it is undefined once again. So at that location, negative pi over 2, it's still going to be a vertical dashed line, a place in the graph where the function doesn't exist. Okay? Now let's actually draw it. All right. Save these coordinates, follow along on a piece of graph paper that will also be available to print. Aside for a moment. What I'm going to try to do is just scan, if I haven't already, a blank of this coordinate plane. I'll show you. Printouts, so you won't have to keep labeling them. There's going to be a coordinate plane that has these labels already on it. I had to try very specifically, very carefully, to make sure that these were spaced as evenly as I possibly could this way and this way. So you notice that it's 3 unit blocks tall between the integers, and along the x-axis I had to make it 4 blocks this way. It's never going to be perfect because we're doing it by hand. All right, but this is on purpose, the way that it's drawn, okay? Anyhow, print out maybe 4 of these, because we're going to do tangent, we'll do cotangent, secant, and cosecant, just so you see it. Put this here, and make sure that this is secure. Keep those inputs, and I'm going to have to duplicate my increments as best I can using this. Okay. Staircase, all right. That's about as good as it's going to get. It's right on the edge of my plywood, that's why it popped. I also knocked it too. Alright, so, taking one of these, first blank, you might want to label it if you want, tangent, this is what the graph will look like. And then I'll show you how to use your calculator. Right. I'm going to have to duplicate, let's see, these increments. I should make them as dark as I can. Make it possible to see. Is that in the frame? Let me dip this just a wee bit. paper that in theory you're printing out, every 4, there'll be an increment this way. Every 4, there'll be an increment this way. Okay. And every 3, there'd be an increment this way. And every 3, there'd be an increment this way. Okay. This is labeled purposely pi over 2. So this would be negative pi over 2. This would be pi, so this would be negative pi. And this would be 3 pi over 2. And this would be negative 3 pi over 2. Remember, these still represent angles. So if you feel more comfortable, right, you could label this 90 degrees, 180, 270, negative 90, negative 180, negative 270, right? And just squeak it on the end here would be exactly 2 pi here, negative, and exactly 2 pi here. All right, the increments that I have running vertically are integers. So this is 1, 2, 3, which makes more sense, right? Negative 1, negative 2, negative 3. I'm going to try desperately not to erase those. So I'm going to do it 800 times. Okay. Let us start with this. The increments, and this is the reason why I say it's not quite going to be perfect because we're doing it by hand, but this first increment that runs here, this first box, all right, we're going to label that in the style of an angle that is a radian, a pi radian. So if you can, squeak it in here, make this first increment understood as being pi over 6. Okay, and the next one, pi over 4, and the next one here, pi over 3. The reason that I had mentioned the decimal equivalents from before is because that would at least be the correct order, right? The spacing might be a little bit off if we're doing this by hand, but pi over 6 would be 3.114 divided by 6, right? And just to remind you, that would be 0.5 approximately. This is a terrible marker, right? Pi over 4 is 3.14 divided by 4, which would be 0.79, which is about 0.8. So it would naturally come after what is approximately 0.6. All right. 3.14 divided by 3, all right, is approximately 1. Right. This is like 0.6, 0.8, and 1.0. Right. Pi over 2, all right, is 3.14 divided by 2, which is what? 1.5 approximately, or maybe 1.6 would be better rounding. Okay, so at least they're in the correct order. 0.6 is smaller than 0.8, is smaller than 1, is smaller than that. Okay, now we're going to basically place a dot. All right, I'm going to do the positives of these first. In these respective locations. Well, at pi over 6, all right, I'm going to go, let's see, is that coincident with the same thing? Pardon me. This is actually 0.5. The outcome is that, all right. So this is like 0.52, this is 0.6 something, all right. 0.5, 0.8, 1.0, 1.6 approximately. Okay. At the location of pi over 6, this is the decimal equivalent of that. All right. You're going to go up as far as you can to place a dot, but being that it is 0.6, it's not going to reach 1. All right. It's not going to be a dot at this exact location here, over 1 up to here, over to pi over 6 up to 1. It's going to be something shy of that. If you figure that these increments are thirds, this is 1/3, 2/3, 3/3 is 1 whole. 0.6 would be just shy of 66666. It's forever and ever and ever. So you would put a dot technically just below this line that you see here. Try to make a prominent dot like that. If on the flip side, I did the negative versions of these, the negative incarnation of these, it would be just this line here. That would be negative pi over 6. And again, just about there would be the dot. I did neglect to do the origin. 0, 0 would be the easy one. And we'd have basically these three dots. 0, 0 at pi over 6, it's about 2/3 of the way up, just a little bit shy of that. At negative pi over 6, just the other side of the 0, would be negative 2/3, so just shy of negative 2/3. So a point here, here, and here respectively. It kind of looks vertical, but it's not. What you'll see is that when you get to the next one, pi over 4, which is about 0.8, now here, from the origin here, you're going to go exactly to 1. Thankfully, we're right on an increment. Right? So you're going to put a dot here. Right? On the flip side, if you went back this way, put a dot at negative 1 for that bunch. Okay, and then we'll do this, pi over 3. At pi over 3, which is about 1.05, whatever it is. All right. We're going to go past 1 because we're going to approximately 1.7. All right, so here's 1. 2 would be all the way up. 1.7, if these are thirds, this is 1/3, 2/3, and 2/3 is 6, wherever and ever. 1.7 would be ever so slightly above that. So put a dot roughly in between the whole 2 and just shy of it. And then, again, on the flip side, you're going to go down to just shy of negative 2. What you're going to see, and it will be more apparent when we do this last one, at pi over 2, there's an asymptote. So I'm going to draw a dashed line through this location of pi over 2. And at also negative pi over 2. Remember, the vertical asymptotes, and this is green, is always crummy. At the vertical asymptotes, the graph is undefined. Okay. Now if I do the fun thing, which is to connect the dots, right? I could get the smooth curve that would stretch horribly squeakily through, doesn't even work, through these points, right? This is what the waveform basically becomes, all right? It's not sinusoidal, all right? That's what cosine and sine would be, sinusoidal, all right? This is instead a sort of staying alive kind of curve, you know what I mean by staying alive? Like staying alive, ho, ho, ho. Don't throw food, please. Least of all through the internet, that would be very terrible. Just get a spontaneously generated pumpkin come my way. Anyhow, this is the basic graph of it. I'm not going to torture you and make you do the rest of them, but if it is a wave, all right, what does that mean? It means that it's going to keep happening, all right? There may be the sudden boundary, all right, vertical asymptote where the graph doesn't exist anymore, but there would be a predictable pattern to this. At every pi over 2, there's going to be a vertical asymptote. So if you wanted to fill in the rest of the picture, which is the reason why I kind of went a little bit further here in the handout. At this 3 pi over 2, at this negative 3 pi over 2, basically the pi's over 2's, all right, put a vertical boundary like this. All right, back here as well. And then you could just kind of cheat, you know. You don't have to be as precise. All right, it's going to go through 0, so it's going to go through pi. It's going to go through whole amounts of pi. Remember, 0 is really 0 times pi, you know. So this is 1 pi, this is negative 1 pi. In theory, it'll go back to negative 2 pi and 2 pi, and you'll have the same curve like this. And you'll see this much of it over here, and essentially the curve this way, like that. It's a lot of people doing this staying alive, right? All right. Why make you go through all of this? For one thing, I'm trying to elucidate how you could translate pi into a decimal if in theory you had to graph this. Even if you made your calculator do it, which I would encourage you to do. All right. Just understand that these are what the decimal equivalents would be. Pi over 6 is about 0.5, right? 1 whole pi is 3.14, you know. Anyhow, let's make sure that you're clear on making your calculator do the same picture, okay? So, in this case, again, as part of the handouts, right, there is, to refer to the instructions from last time, there is, what is this? I don't have it, no idea. There's this sheet with that chalk and the triangle band, all right, which is instructions to make your calculator. Firstly, set it to radians, all right, and then control it manually what you want the dimensions of the coordinate plane to be, all right. I had, remember in here, I made, what is it, the vertical axis between -5 and 5. You could change it, like in this case you notice that I only went up to +3. That might work better, make a more satisfying picture. A lot of times they end up distorting the image if it's a little too much. But this is just suggested for the dimensions here. All right, and here is for evaluating. All right, let's see, like if you want to hit trace, right, and go to some point of the curve. Read the x dimension, read the y dimensions for values. Okay. Let's see. Clear. Let me just make sure that my settings are correct. I'm going to go to mode, in radian mode. That's cool. All right, I'm going to click out of here. Now I'm going to go, again, these two features, window and zoom. Think of this as being the automatic and the manual transmission, right? Sometimes manual is better. I had messed around with this last time. Let me see. And I'm going to correct it, all right? I'm going to make one extreme along the x-axis -2 pi. That's what the decimal is. And then I adjusted it to 7 just because it wouldn't fit. Incidentally, if when you're graphing, right, if you're trying to get some value beyond the scope of the graph, right, that is on your screen, just change it manually to be a little bit longer, right? And if you get an error message, it just means that it's beyond the scope of the screen. You have to adjust it manually, if not automatically. I'm going to change what would be 7 here for x maximum to be 2 pi, so it'll be 6.282 pi. And you see it, that's how you type it, and this is what it enters, all right? The scale should just be 1. Oh, I made it pi over 2. Yeah, I made it pi over 2. Okay, did I make it that? Yeah. All right, the scale is in halves of pi. That's what 1.57 is. It's 3.14 divided by 2. Make the maximum and the minimum, -3, maybe 3. Scale of 1, and that's it. All right, now if you hit graph, if there was something in there, this is the work from last time, you see that it's drawing. These increments that you see here are pi over 2, right? The only downside to this is that unless you force it to, your calculator is not going to draw the asymptotes. All right, let me clear this out. Here's the junk that I had from last time. I'm going to clear it out. Clear. All right. And what I'm going to do is I'm just going to type in tangent. So tangent, I'm going to use the variable x. So x tau theta n is preset to x. And I'm going to hit graph. here you see is the same graph. Goes through the origin, goes through pi, goes through 2 pi, and it curves, right? The imaginary line that would be stretching vertically through this increment right where my finger point is, that's negative pi over 2 and pi over 2 respectively. If you want, there are settings that you can do to graph vertical lines. It would be going through app, right? It might be overkill, right? But if you hit app and you scroll through this, there is a feature which is called in equals. I'll just show you where to get it. This is assuming the software is up to date. There it is. In equals, which allows you to graph vertically as well. It also allows you to do inequalities. If you want to use these symbols, you could press these buttons that are respectively underneath them. It's preset to equal, all right? Notice that up in the corner here, there is also x equals. If you go up to here and then press enter, you could insert what the value would be for the vertical asymptotes. You could do several of them. You'd have to, unfortunately, do several of them because it's not going to understand that these should be repeated asymptotes. I would enter pi over 2 in this particular case. So I'm going to hit, let's see, second, and then caret, and then division, and then 2. And what you'll see when I go back to the graph is that it will at least put one vertical line where it's supposed to be after it's done with the trig function and specifically. No, there it is. It's not dashed, all right? So you're going to have to, unfortunately, change whatever settings if you wanted to make it dashed instead. I believe there's a way to do that, but I don't want to tinker with it right now. Anyhow, notice it didn't do the other ones. Why? Because it doesn't understand that this is an asymptote. Right? Anyhow, it gets really, really close to it. If I go back to this, right, go into x again, and then do the same thing. All right, here, I would have to hit negative second pi divided by 2, and then hit graph. What did I do? I erased it, didn't I? Oh, okay, just went to y. Okay, here's our tangent again. And there's the two vertical lines that should be dashed here. Let me see if I could change the shade. No, quit. Function 1. Okay. Yeah. And if I could do that. I don't know if I want to. No, don't mess with this. Okay. Not right now. Okay. Anyhow, here's a vertical asymptote. Here's the second one that we strategically placed. You could do it again here. You could do it again here. Most importantly, if you want to get the cursor to show up, you can use it to trace out what the x and y values would be. So if you hit trace, all right, as long as you're on the curve, all right, you could scoot this over and examine what the coordinates are. It's going to unfortunately give you the decimal equivalent rather than what the radian equivalent would be, pi radians. But as long as you understand what that correlates to, that is 3.14 divided by some number, right? You could see what it should be. Right. Now notice something, it just jumped. This is a negative y value, and then it's suddenly a positive y value. How come? Because it skipped over the undefined area. Here's another interesting thing. If you hit second and then table, you could see what the input variables, the input values and the equivalent y values would be. If you scroll up and you see an error message anywhere, that's the point of where it would be undefined for the y's or the x's. Let me see. Here's 0, 0. It seems to be skipping over them naturally. Yeah, unfortunately. All right, I'm gonna change my settings So if you want to get out of n equals, and sometimes graphing something is a little bit easier without it, believe it or not, I'm going to have to go back to the list that is apps, right? And scroll down the list. And my calculator's crashing, unfortunately. To get to n equals to turn it off. That one, and then quit. It's a nice feature, but it's a little clunky sometimes too. So if it makes more sense, do intentionally turn this off. Okay, I'm gonna go back to y equals, quit. All right, notice that the x is no longer up in the corner. All right, there's no options for inequalities. So when you're graphing, you just see the curve. Okay? All right. Now, to expedite things, let me just make sure you're clear on this. There should be for tangent, this is specifically for a tangent graph, an asymptote, a vertical asymptote at basically every pi over 2, right? I would be nicer if I used some kind of a formula, but you get the idea. I mean, wherever you see a fraction of pi over 2, even if it's part of this, all right, put the asymptotes there. In theory, even pi would be pi over 2 times 2, all right, but not whole pi's. Don't put the asymptotes at whole pi's. Alright, I'll probably live to regret this, but let me erase this so I have a nice clean surface. Alright, we're not going to brute force the calculation anymore. I think once it's sufficient, you get the point. Waka, the point. But let me show you the other ones. If you want, all right, again, taking a blank coordinate plane, let's do cotangent. All right. I'll give you some fun facts about cotangent. Put this here. Cotangent, which we're going to call y equals cot of x. And in theory, if you wanted to translate cotangent into one of the original 3 functions, then it would be the reciprocal 1 over tangent of x. That is in theory what it would look like. All right, but this is sufficient. All right. In comparison, having discussed tangent, it is appropriate now to talk about cotangent because they are reciprocals. All right. What that means is the vertical asymptotes are going to shift. There's going to be asymptotes at basically every pi. So if you're going to draw, all right, I have my increments like this. That's pi over 2. That's pi. That's 3 pi over 2. And that would be 2 pi there. 1, 2, 3. Pi over 2, negative pi. 1, 2, 3, 4. Negative 3 pi over 2. 2, 3, 4. Negative 2 pi. At every, red probably shows up better, unfortunately. At every pi, on a blank, draw an asymptote like so. Whole pi's, wherever you see whole pi's. Even on the y-axis itself, which would be 0 pi, of course. That's 0x. I'm just going to kind of draw a phantom graph here don't draw this, what I'm about to draw. I just want to show you the relationship, all right? If this is normally what we have asymptotes at the halves. And this is what tangent we've discovered looks like. It goes like this. All right? Because of this relationship, because cotangent is a reciprocal of tangent, all right, the asymptotes end up shifting over, and what you see instead are graphs that look like this. You're going to have that same curve, all right, but it's going to be backwards and shifted over slightly. So you're going to see a curve that looks like this, right, between these asymptotes. Put dots basically at the halves. Okay. That's the only one that really you need to worry about too much. And you'll have graphs that look like this. Graphs is not a word. It looks very much like tangent, it's just shifted over, it's at a phase by 90 degrees. And this situation, right? Basically, where tangent is increasing, cotangent is decreasing. I'm going to draw in black what would have been tangent. Tangent would have been running like this, right? Where tangent is on the upward swing from, say, here at 0, 0 up, notice what's in blue. Cotangent is on the downswing. Okay? Let's do secant. These are fun. I like to do secant and cosecant especially because there's a technique to it, really. I'm going to try to preserve some of this. Save the pies. Save the humans. That should be a bumper sticker, right? Especially at this point. That's actually from Bill and Ted's Excellent Adventure. There was a bumper sticker like that. Anyhow, I'm going to keep labeling this like I had it. Pi over 2. 1, 2, 3, 4. 3 pi over 2. That's roughly 2 pi. 2, 3. Pi over 2. Negative. 1, 2, 3, 4. Negative 3 pi over 2. And that's still negative 2 pi. Okay. For secant, right, which is, we're going to call it y equals the secant of x. Right? Being that it is the reciprocal of cosine, in theory, you could type this into your calculator. Right? It would work. Right. What you're going to do, if you were going to do this by hand, and just to sort of, even if you do it with your calculator, just to give you a feel, right, you're going to start with sort of a cosine skeleton, for lack of a better phrase. Right? In other words, I'm going to try to draw cosine in the traditional way. Put that back, it doesn't work nicely. And I'm going to do it very, very faintly. Now, first of all, I should complete this. I have it incremented as being 1, 1, 2, 3, 2, 1, 2, 3, 3, and this is negative 1, and that's negative 2, and this is negative 3. Under normal circumstances, these points would be relevant. So since I'm going to borrow from cosine to begin with, at 0, 0, right, cosine is 1 for y. At pi over 2, 90 degrees, cosine is 0 on the x-axis, right? 0 on the y-axis, technically. At the location of x, pi over 2, y is 0, right? At pi, all right, cosine is -1. And at 3 pi, it's 0 again, because it's sinusoidal. And at 2 pi, it's 1, right? There would, in theory, be, you know, a maximum of 1 and a minimum of -1 under normal circumstances. Basically, draw this curve, right? Since this is derived from cosine, right? Those points, 0, pi over 2, pi, 3 pi over 2, 2 pi, that is 90, 180, 270, 360, would produce this curve, right? And do it backward. Pi over 2, pi, 3 pi over 2, -2 pi. Draw a curve like this, right? What is in blue is the cosine, all right? How does that relate to secant? Well, secant is going to have vertical asymptotes simultaneously. So basically, do this. Draw asymptotes at every pi half again. So through pi over 2, I'm going to put a vertical asymptote like this at -pi over 2. At 3/2 of pi. At -3/2 pi. I'll wear it. Okay. I just need those boundaries. Basically, what is really going to be cotangent is going to be, now I'm going to purposely make this dash because it's really not supposed to be part of the graph, it's just a skeleton. What is going to be secant is basically going to be the tops, the very peaks of these. I'm going to do this in black. Draw sort of a U shape, sort of a parabola shape. All right, touching just what would have been the top here. All right. And this will be the peak here. And this will be the peak here. And this will be half of it because it's off the page. And this will be half of it because it's off the page. Right. I needed a cosine skeleton to basically establish what the minimum would be and what the maximum would be, what the minimum would, what the minimum would be, what the maximum would be. Okay. This is basically the graph of secant. And similar to cosine and cotangent, there's this relationship where cosine would be increasing, secant will be decreasing. And also, where cosine is 0, secant is undefined. Okay. Notice in the blue line here, cosine is 0 at pi over 2. Well, here's that dashed line. That is where the secant curve in black would cease to exist. Right? Just a little bit to the left, you'd see that it's up here. Just a little bit to the right, you see that it's down here again. Here's the last one, cosecant, which is very similar. It uses a sine skeleton, if you will. So maybe whip out another blank of this if you're going to do it by hand. I'm going to have to correct this again. Let's see. Let's see. 3 pi over 2, 2 pi, and backwards, pi over 2 negative, negative pi, negative 3 pi over 2, negative 2 pi. And I still have it incremented as being 1, 2, 3, and this is negative 1, negative 2, negative 3. Just, again, probably overkill, but that makes it a little bit easier. Alright, here's cosecant, which is abbreviated like so. CSC, sounds like one of those NBC shows, right? CSI Miami, one of those stupid things. I don't like crime dramas, they make me sad. This, again, since you're limited in terms of what type of buttons you have, take advantage of the fact that this is the reciprocal of sine. So if you absolutely have to, right, enter this into your calculator. 1 divided by sine produces this. And similar to before, we're going to start with a sine skeleton. Alright, so I'm going to try to draw it very faintly in blue. Alright. Here's the ceiling, basically, of a sine function. Here's the basement. Alright. And the points that are good to know by heart for sine waves is 0, pi over 2 is up here, 0 at pi, negative 1, right? 0, and you'd have a curve that looks like this under normal conditions. If I did it backwards, all right, negative 1, 0, positive 1, 0. It's sinusoidal into infinity, all right? Again, I really should just keep this as a dash curve because it's really not part of the graph. I'm just using it because I need a skeleton. Okay. Right. We're going to, once again, right, put the asymptotes at approximately every pi. Let's see. Well, it should be every pi in general, not approximately. It is pi. Pi again, right? Whole pi's, I mean. So I'm going to put a dashed line through pi, basically like this, and through 2 pi in theory, through 0 pi, which would be the y-axis really, through negative pi, and through negative 2 pi. Okay. It is a very similar graph to what you had seen for secant, right? It's just out of phase by 90 degrees. One is a cofunction of the other. But I need the peaks again, all right? Draw sort of a parabola shape that goes down to the maximum of what would have been sine. Sine is normally just the maximum of 1 and a minimum of negative 1. So you'll see graphs like this. And it looks almost exactly the same thing, right? It's just shifted over in theory. Okay. What is really the function, just bear in mind, is what is in black. That's the most important thing, what is in black. And the reds are just asymptotes, and the blue is just the skeleton of where it comes from. Okay. Yeah. All right. If you're curious, all right, notice. Put this in green. My greens never show up. All right. Just for the sake of comparison here, if you notice on the sine curve, right? As sine is increasing, what simultaneously, starting from the same point, is the cosecant doing? Cosecant is decreasing. As sine is decreasing, cosecant is increasing. right, from this point. I'm going headed off in opposite directions vertically. Okay. All right. Now, here's the last thing I'm going to point to. Well, let me just walk you through, because again, you're not going to normally draw these pictures. I just wanted you to have the experience. Entering this, all right, making sure that you understand that it's really cosecant with your calculator. Okay, this is what the picture ought to look like. These are the boundaries. I've already had the calculator set to radians and the increments are where they should be. So we're going to go into y equals, turn it on first, Francis. Okay, on. I think my battery might have died. Oh no. Yeah, no. I'm pressing the wrong button, that's why. I keep getting in trouble because the view of my camera here is exactly the mirror image, so I'm like, you know, what are you doing? Anyway, forgive me. I'm going to clear out tangent. So we would have a nice clean graph. The increments are the way we would like them, at least the way I like them. And in here, because there is no cosecant, no cotangent, no cosecant or secant, I'm going to use the reciprocal because I have to. Right? Unless you have a more sophisticated calculator that compensates. You could just do 1 / sign, right? Or you could be fancy. I'm going to see how fancy I can get away with being. Alpha F1, I'm going to enter things in the intuitive top comma / bottom, you know, numerator, denominator. All right. 1. And then down here I'll type sign, variable x, and close the parentheses, and scoot on out of there. Okay, now graph. Let's see what we get. Get these nice loops. Okay. Now again, it doesn't understand or doesn't draw the vertical asymptotes, right? There's settings you could do to make it do that, but you understand that it's at this increment here, which is pi, there's a vertical asymptote where it's undefined. If you wanted to try to trace, let's see if we can get over there. Right, it's going to be automatically on the function. You can, at this point, right, enter an x value. So if I were to enter exactly pi at this point, it's probably going to give me an error message, but let's see. Second pi, right, which is right here, right? Well, I'm reading it backwards. It would be right here. All right, see what you get. Let's see. It did compensate. See, it does put the y when it leaves it blank. All right, how come? Because there is no y value. It just doesn't say, sadly, it doesn't say it's undefined, all right? But it is, all right? If you did 2 pi, all right, here's second, well, there's pi again. All right, here is 2, and then I'm going to put in 2 pi, all right? And you're going to see it's going to do the same thing. The y will show up here, but it'll be blank. Now it gives me an error message. I don't know. Okay. Oh, why? How come, I should say. If it's giving you an error message, it's because of the window settings. All right, yeah, let me out of here. If you go to window settings, look what I made the maximum. Even though it shouldn't be a problem, right? The calculator is only as smart as the dope who's programming it, right? So again, this is a situation where this is exactly the x maximum is 2 pi as a decimal 6.28. If you want to, just to get it to do what you want, just change it to one number higher, 7, all right? Then go back to the graph. And now it won't give you an error message. It will show you basically, oh, it's undefined, right? Hit trace first. Your x shows up. 2, second, and it will spit out what y should be, which in this case, since it's undefined, at 2 pi, right? You'll see it's a blank y. No error message now because I stretched the screen a little bit wider. Okay. Okay. Woof. Right. There is a handout, the last one, which summarizes some fun facts, right, about tangent. Right. these are the ones that I want you to really sort of emphasize. I put this in highlights here, all right? When you have a tangent function that's not too complicated, maybe it has a coefficient a, maybe there's a coefficient of the variable that's the input x, all right? This is the period. Actually, it's the period in both cases. See the period down where my pinky is, right? Is pi over the absolute value of b. And the same thing here, pi is equal to, period is pi over the absolute value of b. But the asymptotes will be a little bit different, all right? Because of stretching, you know? So here is kind of the worst case scenario, all right? When you have the full-fledged transformation, you know, that it's something a little bit more complicated than just a factor in here. If you have these extra features, all right, use this if you want to calculate the asymptotes, all right, by algebra rather than graphically, all right. You would enter whatever the c value is over the b value plus pi over 2 times the absolute value of b, all right? And then there's this k factor. K is an odd integer, all right? This is telling you where the vertical asymptotes would be, all right? Reserve this formula for this more complex incarnation of tangent, all right? Reserve this formula, all right, for this dumbed down version of the transformation, all right? In this instance, you see that the factor that you multiply, k here, it's just an integer, okay? Not an odd integer per se. All right. Let me just sort of like tie this all together with a nice string here. We'll give you some, what you should know, right, about this stuff, right, at this point. To summarize. I'll have to move my graph paper. There is at the bottom of that same handout I was just pointing at a little table that I would have given you to sort of write some fun facts here to know. And I'll write it here. This will be a nice summary. So basically what I'm saying is on this sheet that you should print, all right, let's fill in this information here, just for reference. All right. Okay. Sine of x. All right. I want to break out the ruler this time. Okay. All right. What you should know, right? What is sine, right? That's how you would actually spell it, S-I-N-E. Sine, right, is basically an unraveled unit circle. Right. If it's an unraveled unit circle, that just means that the radius value would be 1. And this would be as complicated a formula as you would have. The R would be the thing up in the front, and it would just be 1 here. So optional to write that, right? What is a unit circle? What does the graph look like? Well, if this is a unit circle, and a unit circle has these key points, right, where you have 0 basically, pi over 2, which is 90 degrees, pi, which is 180 degrees, 3 pi over 2, which is 270 degrees, and then back again is 360, which is 2 pi, right? That translates to this curve. This is the same points stretched out onto the curve. If you memorize this information, it's a way of calculating sine function at those specific degree values without typing it, right? The maximum is always going to be +1. The minimum is going to be -1. right? That's what this traced line is. Why is it 1? Because it comes from a unit circle, right? And a unit circle is 1, so even if the radius rotates from the center up to this point, right, it's -1, 0, +1, 0, -1, right? The radius will always be a whole, will always be a positive integer, right? The absolute value. But in terms of this stretched out graph, right, that's what the value would be. What I'm getting at is that if you, in lieu of a calculator, wanted to know what the sign of 0 is, on the graph, what's the y value? It's 0. If you wanted to know what the sign of pi/2 is, right, on the graph, what is the y value? +1. What is the sign of pi? Right? On the graph, it's 0. Right? What's the sign of 3π/2, which is this point here? It's -1, right? And then it's sinusoidal, it repeats. Right? What's the sign of 2π? It's 0. Right? If you memorize certain information, which you should never shy away from, right, it'll make it easier to make predictions, right? Use your calculator to validate, right? So here's the proof, right? If you entered sine of 0, what do you get? 0. If you entered the sign of -π/2, should be +1, what do you get? Positive, I put negative, sorry. Negative would logically be the same thing too if I drew the picture backwards, but if, quit, sine of regular positive pi/2, dopey. Sine of pi/2, positive pi/2 is +1. What's the sign of pi? All right, should be 0 again because it repeats. 0. All right. All right. The sign of 3π/2. It should be -1 because that's what the graph predicts. -1. All right. You see the point? Okay. I didn't give you a lot of space for this. This is more or less reiterating what you had done the day before. So, what to know about sine? Essentially, most essentially. Essentially, it is an unraveled unit circle. Okay. What to know about cosine? Right. It's an unraveled unit circle as well, but in relation to sine, cosine is a sine wave. I don't know if this is going to be faint. There's a sine wave. Let me see if that's in frame. You can kind of see that. Out of phase, meaning shifted by 90 degrees, which is pi/2. That's the only difference between the two graphs, right? It's just scooted over slightly. Right? It's still the same waveform. So we say it is out of phase by 90 degrees. They're co-functions. Hence the prefix co. Right? What's to know about tangent? Tangent, again, would be spelled like this. I spelled it correctly. Cotangent is the ratio. Let me put this in red, it's the contrast. Is the ratio of sine over cosine. You can see how these things all relate to one another. And if you know the most basic one, you can figure out the others that follow it. Right? It's a ratio, so it's basically these two things divided. Okay. Moving right along here, what is cotangent? And you don't have a button for this, but you could figure it out. Right? Cotangent is spelled like this. Let's see. The reciprocal of tangent. If it's the reciprocal of tangent, and tangent is itself a ratio, then it's cosine sitting on top of sine. It's this flipped. And that means when you're entering this into your calculator, right, you're really writing that because you have to. There's no button. Okay. Last two. Secant. Secant would be spelled like this. And again, it is a reciprocal. But it's a reciprocal of which? It's a reciprocal of cosine. Alright, which means that when, again, you're entering this in your calculator, you would have to write it like that. Or type it like that. Lastly, the cosecant, which is abbreviated as CSC, is spelled cosecant. Is the reciprocal of sine. Of sin. That's the abbreviation, of course, for sine. Sin. Math is evil. And you would write 1 over the sine of x when you're typing, when you're entering this into your calculator. Okay? Those are the most fundamental facts about these things. And again, if you understand, really grasp sine well, that it is a wave, first of all, and the wave just originates from unraveling the circle. The circle could be measured in degrees, the circle could be measured in pi radians. All right, then you can basically memorize key points of the wave, and it will tell you what the cosine, the y value would be equal to at that point. And it's really going to be positive 1, 0, negative 1. All right. Everything else is derived from that concept. Okay. That is section 8.2. And we're basically done with this stuff. All right. For homework, again, keep working in my open math because the practice sections, and if this is A2, practice A2, right? I'm going to examine it to see, which problems to do out of the whatever 10 or so. All right. I would say spend as much time as you possibly can with the My Open Math material because you need the practice. All right. Okay. And try to draw these graphs by hand, right? Using the tables and such, the graph paper, right, that I have available for you. Okay. Thank you, guys. Be safe out there.